Today I want to present this nice result that I found on the Math Stack Exchange. So you can find it pretty easily. It's numbered like this, 2630068. So if you just Google this, you'll find the result. Okay, so let's look at the claim. We'll prove that the sum as n goes from 1 to infinity of the reciprocal of the least common multiple of the numbers 1 through n not only converges, but converges to an irrational number. And to do this, we'll use the following three facts. So the first one we'll prove, and this is like an elementary number theory fact, that the LCM of the numbers 1 through m over the LCM of 1 through n and the LCM of 1 through m over just n is a natural number if m is bigger than or equal to n. And then next, we'll use something called Bertrand's postulate, which says for all primes p, there is a prime q that is strictly between p and 2p. And then the third one is that there are infinitely many primes of the form 3k plus 2. In other words, that are congruent to 2 mod 3. So I have an old video on the channel where I proved this third one. Maybe if you post a link to it in the comments, I'll pin that comment. Okay, so let's get to the proof of this first. So let's notice that if m is bigger than or equal to n, then we have the LCM of 1 up to m is in fact equal to, well, itself, but I'm going to write it like this, the LCM of 1 all the way up to n all the way up to m. That's because n is somewhere between 1 and m. But then by the definition of the LCM, this is going to be a multiple of n, because it's a least common multiple of all the numbers in this list, but n is on that list. Okay, but that means that this equals to maybe kn for some k, which is a natural number. But now we can just do this quotient right here. So we've got the LCM of 1 up to m over n is the same thing as kn over n, but that's equal to k, which is a natural number. So in fact, we've got this second object is a natural number. And moving on to this first one, we can do that using the recursive definition of this LCM. So let's notice that this LCM of 1, 2, all the way up to m is the same thing as the LCM of the LCM of 1 up to n, and then n plus 1 up to m. Again, that's by the recursive definition of the LCM of more than 2 objects. But notice that means that this object right here is equal to a multiple of the LCM of 1 up to n. But that's exactly what we need in order to have this first object be a natural number, following the same kind of argument that we did up here. Okay, so now that we've got this first fact taken care of, we'll move on to our main result. We won't worry about this second one as it's really outside of the scope of what we want to do here. Okay, so we're going to first show that this thing converges. And so we'll do that by taking our series and bounding it above by something. So since it's an infinite series, that means we can think of it as an increasing sequence, but then by the monotone sequence theorem, if we bound it above, we're good to go. So let's take our series. The sum as n goes from 1 up to infinity of 1 over LCM 1 up to n. And let's split off the first term. So splitting off the first term, we have 1 plus the sum as n goes from 2 up to infinity of 1 over the LCM of 1 up to n. So like I said, that's just splitting off the first term. But now that's going to be less than or equal to 1 plus the sum as n goes from 2 up to infinity of 1 over the LCM of just n minus 1 and n. And why does that inequality hold? So that's because the LCM of n minus 1 n is less than or equal to the LCM of everything between 1 and n. So this inequality is pretty easy to see, and then taking its reciprocal gives us the following inequality. Okay, nice. But now we use the fact that n minus 1 and n are relatively prime, which means the least common multiple is just the product, to see that this is equal to 1 plus the sum as n goes from 2 up to infinity of 1 over n times n minus 1, like that. But now re-indexing, we have that this is equal to 1 plus the sum as n goes from 1 up to infinity of 1 over n times n plus 1. And now we can replace this n plus 1 with n, and we'll push the inequality in the same direction. So this is less than or equal to 1 plus the sum as n goes from 1 to infinity of 1 over n squared, which is known to converge. So that means we have bound our series above by something converges, which means our series itself converges. Okay, so that's good. So now we have convergence. Now we're ready to show that this, in fact, not only converges, but it converges to something that is irrational. So we just finished showing this converges. Now we're ready to show that it converges to an irrational number, and we'll do this by way of contradiction. So let's say, by way of contradiction, we will suppose that the sum as n goes from 1 up to infinity of 1 over the LCM of 1 up to n converges to a rational number. So we have a over b, where the GCD of a and b is equal to 1, and a and b are natural numbers. I guess since we're saying that their GCD is 1, it makes sense that they would have to be natural numbers. Now, in parallel to these numbers a and b, I'll define two sequences. So those sequences I'll call a sub n and b sub n. And they will be defined by the sum as k goes from 1 up to n of 1 over the LCM of 1 up to k is equal to an over bn. So in other words, it's like the sequence of partial sums. Now, clearly we know that this is a rational number regardless of the fact that this is a rational number, because it's a finite sum of rational numbers. And finite sums of rational numbers will most definitely be rational. Furthermore, we'll put the condition on this that the GCD of an with bn is 1. So in other words, they're relatively prime. And now I'm going to make a list of primes that are bigger than b, and that list will be infinite. So let's take P1, P2, P3, etc., bigger than b, such that all of these Pm are all primes. Great. And now I want to notice that there is an infinite subsequence of these primes that are all congruent to 2 mod 3. That's because there are infinitely many such primes that are congruent to 2 mod 3. So I'll just write that down here. So infinitely many of these are congruent to 2 modulo 3. So that's important to notice. Okay, nice. The next thing that I want to notice is that for all m, we have Pm is less than Pm plus 1. So we know that because we're putting these in order. Well, maybe I haven't written that we've put these in order, but maybe if I changed how I write this, it would be clear. So let's maybe fix that. Okay, so that's better. Now it's clear that we have these primes in order and they are larger than b. But that means that Pm is less than Pm plus 1. And then by Bertrand's postulate, we know that that is less than 2 times Pm. Okay, but now we can subtract Pm from all parts of this inequality. We only really need to subtract it from these two parts of the inequality, and we'll be left with Pm plus 1 minus Pm is strictly less than Pm. Again, that's from subtracting Pm from here and here. But now I'm going to change that strict inequality to a non-strict inequality by subtracting 1 here. We know that because everything is happening over rational numbers. And now I want to point out the following. If PM is congruent to 2 mod 3, this inequality is in fact strict. So in other words, PM plus 1 minus PM is strictly less than PM minus 1. And how can we see that? Well, we can see that by reducing mod 3. It's clear that we need to reduce mod 3 because we've put this restriction on the prime in the first place. So let's do that. So note, if PM plus 1 minus PM is equal to PM minus 1, so we want to show that we have to have a strict inequality. Okay, now let's reduce this mod 3. And we'll see that PM plus 1 minus 2 will be congruent to 2 minus 1, which is 1 mod 3. So again, that's using the fact that PM is congruent to 2 mod 3 and reducing this mod 3. But that tells us that PM plus 1 is congruent to 0 mod 3. But that's a real problem because that means that 3 divides PM plus 1, which of course is not possible unless it's the prime 3. But there are infinitely many such primes where this is impossible. So there are infinitely many such places where we get this strict inequality. Okay, so that's an important thing to hang on to. There are infinitely many places where we get this strict inequality. So let's just put that here. So this occurs infinitely many times. Okay, so we'll keep that in mind as we move on to the next step. I've got my summary of what we did on the last board up here. So we've got A over B, which is our rational number in lowest terms of the sum which we wish to show as irrational number. We've got AN over BN, which is the rational version of the finite partial sum. And then finally, we've got this fact that for infinitely many primes PM bigger than B, we have PM plus 1 minus PM is less than PM minus 1. Now we're ready to do our calculation. And that will start with A over B minus A sub P1 minus 1 over B sub P1 minus 1. So that's the entire sum minus this special partial sum. So that's going to give us a tail. That'll be the sum as K starts at P1 and goes to infinity of 1 over the LCM of 1 up to K. Now I'm going to take this and multiply and divide by the same number just so that I have something to work with. And that will be 1 over the LCM of 1 up to P1 minus 1. And then we'll have the sum, K goes from 1 up to infinity of the LCM of 1 up to P1 minus 1 over the LCM of 1 up to K. Like that. Sorry, this should start at P1. And now I'm going to rewrite the single sum as a double sum. So I'm going to have 1 over the LCM of 1 up to P1 minus 1. So that's just bringing that down. And then the sum as M goes from 1 up to infinity of the sum as K goes from PM to PM plus 1 minus 1 of this same thing. So we have LCM 1 up to P1 minus 1 over LCM 1 up to K. So let's notice this is just adding everything up starting at P1, but this is adding them all up in chunks based around those primes that we defined on the last board. So the first chunk goes from P1 up to P2 minus 1. The second chunk starts at P2 and goes to P3 minus 1, but it's capturing exactly the same thing as this, just kind of chunked together. Okay, so next up, let's see that this numerator, that's the LCM of all of the numbers between 1 and P1 minus 1, which means it is a multiple of all primes that are less than P1. Because, well, it's a multiple of all the numbers between 1 and P1 minus 1, but that means it's going to include all of the primes there. Now, furthermore, this guy right here is a multiple of all primes that are less than PM. That's because K starts at PM here. Okay, but furthermore, by this guy over here, we know that the reciprocal of this is a natural number, which means this is the reciprocal of a natural number. And we can see that all of these first primes will be canceled by these green primes, leaving us with just P1 to PM in the denominator. So let's write that down. We have this is less than or equal to 1 over, we have the LCM 1 up to P1 minus 1. And then our sum as m goes from 1 up to infinity. And then our sum as k goes from PM up to PM plus 1 minus 1 of 1 over P1 up to PM. Next up, we want to make the important observation that this portion of the sum does not depend on k. The inner sum is indexed by k. So we can bring it out, and then we're just adding 1 to itself this many times between PM and PM plus 1 minus 1. But that's exactly PM plus 1 minus PM. So we have this is equal to, let's put it down here, 1 over the LCM of 1 up to P1 minus 1, just bringing that down. And then the sum as m goes from 1 up to infinity of PM plus 1 minus PM over P1 up to PM, that product. Okay, so again, that's just from the fact that we can bring this out, and then we've got a sum of a constant there. Next, we'll use this third fact, that this numerator is less than PM minus 1 infinitely many times. So that means we can have a strict inequality here, because we get that strict inequality infinitely many times of 1 over this LCM of 1 up to PM minus 1. And then the sum as m goes from 1 up to infinity of PM minus 1 over the P1 up to PM. So we're left with that. Okay, so let's bring this here, and then we'll start towards the end. Okay, so on the last board, we had the following inequality built. A over B minus AP minus 1 over BP minus 1 was less than 1 over this LCM, and then the following sum. I put that the inequality is bound on the left by 0, because clearly this is an increasing sequence, the sequence of partial sums, because it's a sum of positive terms. So if we take the final value minus any of the partial sums, we will get something that's most definitely positive. And now I want to explore this sum a little bit, and notice that it will telescope. So let's first look at the m equals 1 case of this sum. That will give us P1 minus 1 over just P1. Okay, and then let's look at the m equals 2 case of this sum. That will be P2 minus 1 over P1 times P2. Then let's look at the m equals 3 case of this sum. That'll be P3 minus 1 over P1, P2, P3. And then plus dot, dot, dot. Okay, now let's expand each of those a little bit. So we'll expand each of those by the subtraction. So we've got P1 over P1, that's 1 minus 1 over P1. And then here we'll have P2 over P1 times P2, so that's going to be 1 over P1, and then minus 1 over P1, P2. So that's what this splits into. And then likewise, this splits into 1 over P1, P2, minus 1 over P1, P2, P3, and then that continues on. But notice we've created some sort of telescoping behavior. This guy cancels with this guy. And then this guy cancels with this guy. And then everything after that will also cancel as well, leaving us this sum right here, which I'll maybe circle in this orange color, goes towards 1, or it takes on the value of 1. Okay, so let's get rid of this little calculation and we'll see why that's a problem. So after telescoping the last series, we ended up with the following inequality. But now let's multiply all parts of the inequality by this LCM to get something a little bit different. So that'll give us this. We'll still have a 0 over here, and then over here we'll have A times the LCM of 1 up to P1 minus 1 over B. And then here we'll have A P1 minus 1 over B P1 minus 1 times the LCM of 1 up to P1 minus 1. And then this is less than 1. Now I want to explore each of these numbers. So let's first explore this number. And notice that by our definition of these primes, we know that B is less than or equal to P1 minus 1. That means that this thing right here is a natural number by this thing that we started off proving at the beginning of the video. And now let's explore this one, and we'll explore it via this definition up here. So we have, this is equal to the sum as k goes from 1 up to P1 minus 1 of the LCM of 1 up to P1 minus 1 over the LCM of 1 up to k. But again, by this result right here, each of those is a natural number, so we're adding up this many natural numbers. So that means this guy is also a natural number. But now we're taking the difference of two natural numbers. So the difference of two natural numbers is always an integer. So we've got that this thing in blue is an integer. Maybe let's give this thing a name. Maybe we'll give this the name capital N. So let's notice what we have. We have capital N as between 0 and 1, and it's an integer. That's most definitely a problem. To be more concrete, we could say that capital N is in the set of the integers intersected with the open interval 0 to 1. There's clearly no integer between 0 and 1, so that is the empty set. And so what we've done is found an integer between 0 and 1. But that's a clear contradiction. And what did we contradict? Well, everything followed from our very first assumption, which was this sum converged to a rational number. So that assumption must be incorrect, and thus this sum converges to an irrational number. And that's a good place to stop.